We often see breathtaking images of distant galaxies online, galaxies located millions of light years away from us. Despite these immense distances, we are able to capture remarkably clear photographs of them. While challenging, this is possible thanks to powerful telescopes capable of observing objects across vast cosmic distances. Up to this point, there are no major issues. The real challenge arises when we encounter images of our own galaxy, the Milky Way, taken from the outside, even though we ourselves are located inside it. So how is it possible to photograph our galaxy from an external perspective while remaining within it? Imagine you are standing inside a large football stadium, holding your smartphone camera. You are asked to take a clear, complete photograph of the entire stadium from the outside, capturing it fully from one end to the other. What would you do? The obvious solution is to exit the stadium, move to a sufficient distance, and then take the photo. This is the standard approach we use when photographing large structures. But can we apply the same principle to photograph our own Milky Way galaxy? To answer this, let's examine the farthest spacecraft humanity has ever sent into space and determine whether that distance is sufficient to image our galaxy from the outside. In 1977, NASA launched the Voyager 1 probe. It visited Jupiter and Saturn, sending back valuable images and data, before continuing its journey beyond the Kuiper Belt and eventually exiting our solar system entirely. The probe will continue traveling through interstellar space until approximately 2036, when its nuclear battery is expected to deplete. After nearly 45 years of travel, Voyager 1 has covered about 23 billion kilometers. While this distance is impressive, is it enough to photograph the Milky Way from an external vantage point? The Milky Way galaxy spans at least 100,000 light-years in diameter. To compare these figures, we must convert everything to the same units. 1 light-year is approximately 9.5 trillion kilometers, or 9.5 followed by 11 zeros. A quick calculation shows that the 23 billion kilometers traveled by Voyager 1 amount to roughly 21 light hours. In other words, it would take Voyager 1 approximately 18,771 years to travel just 1 light-year. That means it would reach a distance of 1 light-year only around the year 20,793 AD. Given that our galaxy is 100,000 light-years wide, it becomes clear that we cannot photograph the Milky Way from the outside using the traditional method of simply traveling far enough away and taking a direct image. Any claim that this has been done in that manner would be inaccurate. However, this does not mean it is impossible to create detailed images of our galaxy while remaining inside it. Recall the stadium analogy. What if, instead of leaving the stadium, we stayed inside and used a different technique? We could capture multiple individual photographs of every section around us: the pitch, the right stands, the left stands, and the opposite side, and then stitch these images together like pieces of a puzzle. The result would be a panoramic view of the entire stadium, giving the impression it was photographed from the outside, even though it was assembled from observations made from within. This is precisely the approach astronomers have used to map and image our Milky Way galaxy. This method of piecing together observations was not invented by modern space agencies. Scientists throughout history have employed similar techniques, gradually refining them as technology advanced. In ancient civilizations, observers noticed a strange, luminous band stretching across the night sky during certain times of the year. It appeared as a broad, glowing river of stars and light. Without telescopes, people in dark locations, such as deserts or remote areas like Wadi el-Hitan in Fayum, can still see this band today. Ancient astronomers carefully recorded these observations and mapped the positions of stars. One of the most influential early works was the Almagest by Claudius Ptolemy, who lived in Alexandria, Egypt. Although not entirely accurate by today's standards, Ptolemy's model and star catalogue served as essential references for centuries. Advancing forward, during the late 16th century, the Danish astronomer Tycho Brahe established one of the most advanced observatories of his time and compiled the most precise and extensive star catalogue of the pre-telescopic era. His meticulous observations of stellar positions greatly improved the accuracy of celestial maps. Brahe's work was later used by his assistant, Johannes Kepler, to develop the laws of planetary motion. During the Renaissance and into the 17th century, astronomers such as Galileo Galilei made groundbreaking observations with the newly invented telescope. Galileo was among the first to resolve the glowing band of the Milky Way into countless individual stars, revealing its true nature as a vast collection of distant suns, rather than a cloudy haze. We continue forward until the European Renaissance in the centuries that followed, when astronomers began making even more precise measurements of stellar positions. Galileo's development of the telescope marked a major leap forward in observational capability.
It was the spring of 1609 in Venice when Galileo learned about a new device, invented by a Dutch eyeglass maker, through which faraway objects could be viewed as if they were nearby.
The first European to attempt a comprehensive map of the Milky Way was the British astronomer of German descent, Frederick William Herschel. In 1785, by combining observations from over 600 different locations, he produced what became known as Herschel's map of the galaxy. More than a century later, the Dutch astronomer Jacobus Kapteyn conducted an even more detailed study, incorporating apparent magnitude, spectral type, and radial velocity data from over 200 observing sites in collaboration with 40 observatories. In 1917, American astronomer Harlow Shapley analyzed globular star clusters and demonstrated that our solar system is not at the center of the galaxy, but rather located toward its outer regions. This required significant revisions to earlier maps. Around the same period, in 1920, Edwin Hubble made groundbreaking discoveries showing that the universe contains many galaxies, which generally fall into three main categories. Elliptical galaxies, roughly spherical or oval in shape, with stars distributed fairly uniformly. Spiral galaxies, featuring a bright central bulge packed with stars, surrounded by sweeping spiral arms. These are the most common type observed in the universe. Irregular galaxies, lacking a defined shape and representing the least common category. Astronomers realized that the prominent glowing band we see in the night sky closely resembles the spiral arms extending from the center of a spiral galaxy. This supported the conclusion that the Milky Way is a spiral galaxy. In 2003, NASA launched the Spitzer Space Telescope, which observed in infrared wavelengths and helped confirm that the galactic center contains a dense cluster of older red stars, with spiral arms branching outward. While the exact number of major arms remains a topic of discussion, data from NASA's NEOWISE mission, launched in 2009, revealed two prominent arms, the Scutum Centaurus arm and the Perseus arm, along with three secondary arms, the Outer Arm, Norma arm, and Sagittarius arm. A smaller spur, known as the Orion arm, branches from the Sagittarius arm, and it is within this Orion arm that our solar system resides. By combining centuries of astronomical observations and modern space telescope data, we have assembled our current understanding of the Milky Way's structure. While not perfect, this represents the best model we have today. If you've made it all the way to the end, thank you. You're part of an amazing audience. Please give this video a like so we know how many of you reached the conclusion. And if any questions come to mind, feel free to leave them in the comments below. Thank you for watching.